Our pal George Smoot is a celebrated astrophysicist and cosmologist. He's recipient of the Nobel Prize in Physics for his work on the cosmic microwave background explorer with John Mather, and an expert on the Big Bang and cosmic evolution. He's a longtime professor at the University of California, Berkeley. Please let's give a big Starmus welcome to George Smoot.
I come to bound out here on the stage to show my energy, even though Donna reminded me of work that I did more than 50 years ago when I was tasked with the problem of how to use radiation to cure cancer, in the sense that I was the only person that had a device that could measure the energy deposition by high energy relativistic particles like protons, helium nuclei, carbon nuclei, and so forth. And as she showed, the nice thing about the protons is they give very little energy until they come near the end of their range and they dump all the energy. Well, guess what? I was the first person to show what everyone here will know is true. The energy deposition goes is Z squared. But in fact, I had built the only device, because we were going to look at cosmic rays from the galaxy to see what was coming to the Earth, that could see helium, carbon, nitrogen, oxygen, and so forth. And so they needed that to try and save a senior researcher who had an inoperable brain tumor. So over the years, I moved to try and using nanoparticles and magnetic nanoparticles. And then eventually, that was 20 years ago, 10 years ago, I started using CAR T cell, getting interested in CAR T cells. And so that's finally getting to the topic here at hand, which is not what you'd expect, and not what Derek expected when he told me, what are you going to talk about? But I told him this is important, and you'll see that we're going to want to make very good, large-scale stem cell therapy centers and cryopreservation centers so that we can bring top-level health to everyone at a really good price. Okay, so that's the point of what I'm trying to teach you today. This is actually part of what I call my ring lectures. Okay, my first ring lecture is we have entered the singularity. This was something forecast by John von Neumann 3/4 of a century ago. He said that when the development technology got to be too rapid for humans and human society to respond, you enter in what he called a singularity. He was a very outstanding mathematician. He knew it was an essential singularity, that it was you're unable to predict what the future would be for humanity. However, you can predict that if we hold civilization together, we'll be, in 5 years, twice as rich as we are now. We can afford to do all these wonderful things. There's going to be a lot of dislocation. We got also climate change coming to deal with at the same time. There had to be an accident. But the things that are going on in the world today, many of them are a result of the fact we're entering into a time when technological things are happening so rapidly, society can't handle it. Some human stations are going to be swept away, and some human laws are going to be moved away. That's part of what's going on. But at the same time, we can be richer, and we can do a lot more things than we have to do. So then the second lecture was the stem cell therapy lecture. That's what I'm going to talk to you about mostly today, but not the full length. And that is, we can provide really high quality medical care for people, including curing cancers really spectacularly, as long as you catch them before they're like big blobs in your head. So we can do that to people, and if we do it right, we can bring the price down to where 70% of the world can afford it easily, and if we actually cooperated, everyone could afford good medical treatment. That's one of the good things that can happen, and that's my good news message today. I have a third lecture about how I learned back when I was thinking early days about the singularity. I helped found Singularity University. One of the things that we worked as a development trying to teach people is that when you're in normal times, you look at the problem today, you see what is cutting edge technology, try and solve that problem. But when you're in the singularity, you don't do that. You look 5 years from now, see what the problems are going to be, and see what technology is going to be available in 5 years so that you can do that problem correctly. So you now have to say, what are going to be important problems in 5 years? How can we handle them? One of the important problems in the future will be people want to live longer and healthier, and they're going to want to be happy about it, and they're going to want to be rich, right? So we got to give people that as a goal for 5 years from now. But getting the stem cell therapy stuff together, that's about a 5-year scale, and we can make it so that almost everybody can get substantially longer, healthier lives. And then if we put in much more effort, we can give everybody much longer, healthier lives, provided we have enough money. That's going to be the problem. And then I'm not going to give the fourth one, because I decided it's two, but that's the right side list, the Twilight of the Gods. But I've done two side things, one of which had 6 million people involved in it. It was people who need to learn to program AI and learn to use AI agents, and then learn to make their own AI agents. That's one of the side talks that I did. The other is taking care of your mitochondria. Right. So that's where we're going. We're going to look at the stem cell, look at the promise of unbelievably good, high quality health care for as many people as we want, and how we're going to do that. This is just a slide saying everything about healthcare is going to be revolutionized because we have big data, we have big computers, we have AI cross-sampling across very large populations. There's a huge amount of things that are going to happen. Here's a slide that I used to show in talks 10, 15 years ago, that when your baby is born, and one of my colleagues in Mexico I convinced to do this, when your baby is born, you want to take the umbilical blood and you want to separate it into the stem cells, and you want to preserve those stem cells so when later in their life, when they need stem cell treatment, you have as good a quality stem cells as you can have, right? So it's in China because I gave a lot of talks in China. This is an ad from one of the companies in Hong Kong, because Hong Kong didn't choose to do it, but rich people can do it, that these guys would come in a car, take your baby's umbilical cord, take the stuff off to a company that will separate out and save the stem cells and store them for you at a regular cost. Here is the progress, the way it looked 10 years ago, on how many diseases were being treated by stem cells, umbilical cord stem cells, and you were supposed to be guessing ahead 10 years, which is now, but the fact is, it's continued to increase. People are able to treat and solve a lot of problems that young children have with stem cells, but now we can do a lot more. Here's the plot up to 2012 of the number of clinical trials of stem cells. Okay, and you'll see it's about 5,000 or something. There's only 1,000 diseases, so that means every disease has got more than one potential stem cell treatment. These are early stem cell treatments and somewhat more advanced stem cell treatments, but they exist. And you can say, well, how is that done? Let's continue on. Here's an example of the pluripotent ones. It turns out one of the things that's done is people have made advancements in it. You don't have to take stem cells from the umbilical cord anymore. You can get it out of your bone marrow, and you can do a lot of things. And you're beginning to see that the number of stem cell clinical trials is starting to roll over a bit, right? We're actually having enough that we're no longer exponentially increasing the number of trials. We're beginning to find some that work, and there's less demand for the new treatments. Now, we can look at the stem cell market forecast, because in the end, we got to pay for this, right? We're not going to just say, oh, this is good, the government's going to do it. Somebody's going to pay for it, somebody's going to make a lot of money doing that, but we're going to make it cheap so that we don't care that they're making a lot of money. It's just, we want the treatments. So if you look, you can see the market is going, and it's been growing more than 25% a year. That's an incredible rate. That's the kind of stuff that's actually going on in many fields right now. There's 6 or 7 fields where the technology is increasing at this kind of rate. That's why society can't handle the rate it's going on. We just have to adjust to it. This is an ad from Hong Kong, because I was in Hong Kong just a few days ago. It's just an ad for stem cell treatments that you can get. And you will notice a lot of it's cosmetic, but a lot of it's real health issues, right? So it turns out Hong Kong is actually the oldest population. The people live longer in Hong Kong than anywhere, more than 85 years. And there's a lot of people in their 80s and 90s in Hong Kong, and they want to look young and healthy. And so that's what they advertise for. This is an advertisement that I see in Mexico. Here they're talking about health, other treatments and everything, but it's advertised towards the rich North Americano, not all of Mexico and all of North America, but it's going to be a case that it's going to be very common in Spain, it's going to be very common in other places. That is why we want to be able to do this, because we want everybody to get extremely good health care at extremely low price. This is them telling you in Mexico what you got to do. You got to give them a sample of something that's good enough to be a stem cell or a pluripotent stem cell, and then they go through and select out the things. They decide what it is you need a treatment for, you activate the cells for that, you multiply the cells, and then you get the person down there, check they're not infected or something, and you inject them with it, and you save some for the next treatment in case they need another treatment. There are 3 countries that are trying to be the low-cost stem cell providers. They are, in alphabetical order, Mexico, Thailand, and Turkey. There are some others. You can look on the left, you can see how expensive it is in the United States. It shouldn't be $20,000 or $50,000. It should be down around a few $1,000s level for getting a treatment that cures your cancer or cures your macular degeneration so your eyes work again. Those are the kind of things that we're looking at for what we want to do. And these are what people advertise in these different countries now, because people are willing to pay for them. This is what the projected market looks like. So Thailand is one of the places where I'm working with people, and we should have in place, it should have already been agreed, we should have in place an agreement to make one of these stem cell centers in Bangkok, or I wanted to do it in the Kars Mountain, but near the center of Thailand, and we're going to make one of these. Now, we're going to see a little bit later on, I'm also in talks with people and trying to get the Mexican NSF to make one in Mexico City. Look at the projected market, China, growing 27% a year, okay? $5 billion within 5 years. This is not small, but worldwide, it's going to be $27 billion in 5 years. So this is not a small market. This is what the computer market looked like in its early days. Exponential rise. Everybody and his brother had to have a computer. In the end, it was the high quality, low cost producers who delivered good products that are the ones that survived, right? That's why Dell Computer's there and Eagle Computer's not, right? That's simple as that. So here's the geographic location of where stem cell treatment clinical trials are going on. It's a lot in the USA, a lot in Europe, and a few other places. In the blow up, you can see where in Europe and see what's going on. The number of sources, the number of places where there are stem cell trials going on is increasing worldwide. I have to put this on the side because I have a separate talk about this. Don't forget your mitochondria, okay? Honor your mother. Your mitochondria came from your mother. They're in there, they're providing energy to your cell. Turns out more than 40% of the things you consider to be aging are actually failures in your mitochondria. You must be taking good care of your mitochondria to make sure you don't age prematurely. Alzheimer's is a mitochondria disease. There's a lot of people doing a lot of tests for what it might be, but in the end, it turns out to be the mitochondria. And you look down, COPD, lung congestion. There's a lot of things, osteoporosis, your knees hurting, right? A lot of that is your mitochondria having not been treated right, like me drinking sugary soft drinks. There are stem cells for regenerative medicine. I have 2 acquaintances that have spinal problems, one in the lower back, one in the upper back. Turns out there are stem cell treatments for that. This picture I put shows you a picture of one of the laboratories where people are generating these. It's wrong picture. You don't want to have all your stuff out in petri dishes with people breathing on it and working around it. You want this all closed and automated. Here's the process. You take a sample, you do something to separate out the T cells. You're going to use these T cells. As soon as you're ready, you unfreeze them. You select out the good cells. You activate them against the particular cancer. You then multiply them like crazy. So you multiply them up from a small number of cells to like 1 million or 50 million cells. And you take some of that and freeze it for future use. And you take the other part in, and they're targeted against the particular cancer you have. Right? So that's the trick. You have to be able to get a piece of that cancer, and you have to introduce something from that cancer to your T cells, and train your T cells to attack that cancer, and then it attacks the tumor, but it also attacks any stuff that's metastasized. So that's way better than surgery. That's way better than radiation. It's the way you really want to attack cancer. So I show you some more. If you look at it in much more detail, it's the same process going on. You've got to get your cell, your stem cell source. You've got to preserve it for whatever you need it. You've got to unpreserve it. You've got to activate it. You've got to make it ready to do the task it's got to do. You've got to multiply it up. And you've got to just inject it in the person. That's the process that we got to take out of the hands of individual people and turn into a overall process that is automated and closed. So no humans are in contact with your cells, and your cells are not in contact with any humans. It's all automated, it's all in a closed system. There is no contamination or no other thing, and we have to turn the efficiency up. This is the one that I paid most attention to because I started working on it 10 years ago. This is the CAR T cell therapy. Your T cells are your immune system cells. You find them, and then you CAR them to attack the individual cancer you have. That is the most efficient, effective way to handle cancers if you have any risk of metastasis. I put my favorite one in because this is another way of doing it, but it includes the little particles. Let me go on. This is the more detail of what the steps are. This is the process that we actually have to treat as a process, not as people shuffling things around. This is then a thing I learned to do when we were doing COVID DMR and trying to measure we had to say, what are the kind of machines we're doing now, and what kind of errors do they have in the measurement? That's on the left-hand side, how well we're doing. And on the right hand, what did we have to do in terms of implementation to prevent errors, cancel errors, subtract out errors, or calibrate errors out so that we can get the errors down low enough. And so I picked the stuff on the left, or the stuff that I think is what exists in the typical system now. On the right is what I thought, if we were making an automated system, we should be aiming for and improving the system to do. And it turns out to be harder than it looks. In the case of the COVID DMR, where we're making the maps of the universe, I had a full-time person whose only job was systems engineer. He had to look at the system in it, had to look at the model that we made, and he had to be checking every time we did something that it was actually meeting the requirements that we put down. That's what we have to do to the stem cell kind of thing. You got to expansion them. When you expansion them, every time you divide a cell, you got about unity chance of having a DNA or other kind of information failure. That's one of the reasons your body tries not to divide its cells too often. What it tries to do is rejuvenate the cells as long as it can before it's forced to do it, because you have a limit, called a Hayflick limit, of how many times you can divide. Your telomeres get too short, and your cells get too many errors, and they do you in. Typically, if you want to get between 1 and 500 million cells, you're going to have to do a lot of divisions, unless you start with a big, good pile. That is, if you stored them and you got all of them back, good, safe and sound, and you can use them, you don't have to make so many divisions. I'm going to show you this actually exists. This is one of the places that I went and consulted cryogenic systems for. And the only thing wrong with this picture is there's humans in it. And on the right, there's this thing, which would be an automated station for creating a stem cell therapy. That is, we're going to take a sample of your stem cells out of one of these tanks, which there are in each tank there's at least 1,000 samples. We're going to find yours, pull it out, put it in that machine. It's going to warm up 1 milliliter or 2 millimeters of your cells and select out the ones that it thinks are good, activate them for a particular treatment for you, and then multiply them up, and then freeze some for future treatment, and give some to be injected in you as the time comes on. And no surgery, no nothing. You gave the sample, we grew the fixer, we put the fixer in you, no surgery, nothing else. They didn't even call you back for a follow-up. They just checked to make sure you weren't infected when they gave you the thing to begin with. You went back and you got cured. That's the treatment. Here's an example of the kind of things. If you look on the right, this is an ad for the CryoArc Deca -190C. That's liquid nitrogen. It's a device that's a big tank. It's got a whole stack of these 2 millimeter samples in it. And it automatic things to move it up and down. You can move it up to you just rotate it around, move it up to one. A robot arm reaches out, pulls it in, takes it and put it in the thing that's going to make into the particular set of lines that's going to make the kind of treatment you need. That's the step that we're going to. And already there are 5,000 such possible treatments. Now you got to figure out how many you want to have in your stem cell treatment center to begin with to make enough money to keep in business. I tried using AI to help me with this. I wrote the description on the left. I got the picture on the bottom on the right. Wasn't so good. It's kind of what I had in mind. But I wanted to have a situation where I have power lines coming in, solar cells on the roof, liquid nitrogen creators, 2 big tanks, full of liquid nitrogen, because if there's a typhoon or somebody hacks all the electronics in Spain, you're not wiped out. You can keep your stuff all frozen and in good shape. And then gravity feed down to these automated systems and AI to watch over it to make sure it's doing great. And so I tried again. I got a much better picture. It looks really cool, but it's not what I was telling them, but it's still got a lot of stuff. But you're beginning to see the scale of what we have to talk about, because we're going to want to eventually be having 1 million and then 10 million samples stored in one of these facilities, because we're going to have that many customers. Here's another example they did, and I had to tell it, no, I didn't want any plants. I'm trying to avoid any contamination. And this is one that finally came closer, because at the time I was calculating, I seemed to be the only person in the world that understood that frozen cells are much more damaged by radiation than live cells. If you start thinking about it, you realize it's obvious. First of all, live cells have high conductivity, electrons can flow and go back. Second of all, you have machinery in your cells for correcting radiation damage, and it can correct a lot of it. And so it turns out there's a lot of data on how live things go under effect of radiation. There's very little data on how unlive things go. There's a whole lot of cells in your body, and it turns out that about 10% of them are close to being stem cells. Your bone marrow is close to stem cells because it's making T cells, immune system cells, and it's making certain kinds of blood cells that you need. Here's the cell size. You see the HIV virus, a bacteria, a T cell, roughly 7 microns, and a human egg cell, which is 10 times bigger, right? The problem is, the bigger you are, the more likely you're already hit by a cosmic ray. You could look at something that's roughly 10 microns on the side, it should get hit 3 times a year by a cosmic ray at sea level. Now, if you're going to store these cells for 10, 20, 50 years, depending on which kind of stem cells they are, you don't think they're going to do well if they get hit by radiation many times. I'm one of the few people that figured it out, and I worked it out in terms of hits, in terms of energy deposited per unit volume, in terms of various things. It is clear that you have to do some protecting of stored stem cells or there'll be a problem. That's why my colleagues here in the second row or third row know I want to do one in Mexico City. Mexico City is at a height of 2.2 kilometers. The radiation load there is 3 times what it is at sea level. You got stuff from the cosmic rays, you got stuff from the ground and the floor and the stuff here is roughly comparable. And you're inhaling radiation all the time because there's radon-222 and carbon-14 in the air. You're inhaling it. And it turns out you eat it too, so your body is radioactive. My body has about 5,000 potassium-40 disintegrations per second. 5,000 per second. Okay? Same for you. Same for you. There's a lot of radiation around, and we have to figure out how to deal with it. Is we're going to have to shield the stored cells against the radiation, both the cosmic radiation and the natural radiation in the environment, and eventually maybe from ourselves, but we'll see. And there's a picture on the right that looks kind of yellowish. Those are electrons. They're a piece of meat, a banana, various other pieces there. When you eat a banana, that's 1% of your daily exposure to radiation. Okay. Now, I like bananas, so I eat half a banana every day, most of it, but we'll see. So the radiation damage in the cryopreserved cells, it turns out I searched and searched. I only finally found one article that gave data, and they did the one relevant experiment. They did an experiment in France which is in the 6-story building made out of concrete with a good roof, 2 sub-basements down, and a shielded laboratory. That's number 1. The number 2 is going up on top of in the mountains in France, plus giving him some calcium and some other gamma ray emitters. And the number 3 is a deep mine with low reactivity shielding and low reactivity metals. And look, you can see on the far right is the best, most shielded. You can see what fraction of the cells kind of died. You can see what they did when they were 10 meters water equivalent underground. And then you can see what happens when they're up higher in the mountain, like in Mexico. And this isn't quite right because their failure rate, they did a pretty good job, but it's for 2 months, 3 months, 6 months. It's not very long compared to the number of years you want to do it. But at least there's some evidence that comes out to give roughly the same numbers that I calculate. We're going to design this. It's going to be engineers. There's going to be a little bit of physicists, and a little bit of chemists, and a few life scientists, but it's mostly going to be like 25 engineers. And you got to make it so that it can be government inspected. It gives people confidence, right? There's a whole lot of things you have to do to make sure this is high quality, but this is nothing outside of what we can do as people, because we now have all the technology and the tools to do this. The conclusions are a beginning. Hopefully, we're going to finally have our thing approved in Thailand, which should have been approved by the end of the year, but it's still dragging to now. And hopefully, with my colleagues, some of whom in the audience, we will have an NSF proposal in to the Mexican government, because you have to have the government supporting it, you have to have the science foundations supporting it, scientists supporting it, and rich people who are going to pay the money to build these big facilities. So thank you.